Okay, so let's have a food chemistry class. And this will be moved on to the real food chemistry material. We're going to talk about chapter 1, the water, and material related to corresponding to the chapter 1. But I want to mention there are some of the mistakes there. So when we talk, we will be mention that. Some of them will be not in the textbook, but I think it's important. So two sections we'll talk about water. This will be water number 1. So water section number 1. First of all, this is everybody knows the chemical structure or chemical symbols of the water is H2O, and the mass weight equals the hydrogen weight 1 multiplied by 2, add the oxygen mass weight, which is 16, so the total is 18. And we also know that the boiling temperature of water is 100 degrees Celsius, but this is at sea level. We'll talk about that real quick. And the density is 1 gram per ml. We know this is at 4 degrees Celsius, if we know the physics. Viscosity and all the others you can see in the table of the textbook. We're not going to repeat it here. So very basic, some of the characteristics of the water, it is, we say it's tasteless, odorless, so no odor and no flavor, tasteless. And we also call it colorless. No color, it is transparent, but some people say there is a slightly blue hue. This could be reflected when you see the ocean. So the water reflected with sunlight, you see a little bit of blue hue. Just for feeling about that. So people say it's a slightly blue hue, but basically it's colorless. Now, biological importance, we already know it is very important for the all biological function. So we're not going to repeat it here, because you know, for the metabolic, for the genetics, from different perspective points, so water is very important. So we skip about that part. We know from the food processing standpoint, water could be drinking water. Beverages could become like a tea, make a coffee, and all the other kind of the beverages. From the food processing, in the different classes, we talk about like produce processing water. We talk about chilling water, and all the others. And from the food chemistry standpoint, I will say water is basically a good solvent, because we want most of our chemicals, antimicrobials, even antibiotics and antioxidants can be well dissolved in the water. And we could very briefly to review what we learned in the biology class. We had a fluid mosaic model of a cell membrane system. Looks like it's a protein and the lipopolysaccharides is intersected with each other. And we talk about these phospholipids. If some chemicals, they can dissolve in the water, and they like water, like the head of the phospholipids, we call it hydrophilic. This means like water. And if some chemical cannot dissolve in the water, let's say fatty acids, it very looks like the tail, we call it hydrophobic. So we just say it's this like water. Okay, so this is the first thing, some basic information. We very briefly to mention about that. Since it's a food chemistry class, so we want to talk about the second thing. This is the first part, I would say. The second part, we want to talk about the chemical structure of water. And we mentioned it before, but here we're going to go much more detail. So what it looks like. Composed by, the water composed by O, oxygen, and then has H. So basically it looks like this. And we mentioned about this angle is 104.5 degrees. And the connection between hydrogen and the oxygen, it is by a covalent bonds. Covalent bond. And we also say this covalent bond is actually a sigma bond. And because of the electron negativity, so remember we talk about electron negativity value, the H is 2.1, oxygen is 3.5, so although they are on the covalent band, they share the electron, but the attraction of the electron will be strong for the oxygen compared to the hydrogen. So we usually write sigma negative, and this is sigma positive, and this is also sigma positive. Okay? And we also know that oxygen and hydrogen, they are sharing an electron right here. Sharing an electron right here. But also the oxygen has two pairs of electrons, which is lonely. So we say, we can draw right here, it is a long, or we say long electron pairs. And we also know the distance of the covalent bonds between the oxygen to the hydrogen here is around 0.10 nanometer. Okay, and we are going to get to this more detail later on. So this is one single water molecule, but you know in the water system, they're going to be connected with another water molecule. So how do you do? So we're going to draw another water molecule right here. Okay, so we can draw right here, just like this. Still the H 104.5 degree, sigma plus, sigma negative, sigma positive, and this is covalent bonds. So how they connected with each other? We talk about they are connected with hydrogen bonds. Hydrogen bond. And we also say this hydrogen bond is relatively weak. That's why the water can be moving. Now, how weak it is, how strong it is, and we talked about earlier, covalent bonds, if we want to break down, this needs 110 kJ per mole to break it. And the hydrogen bonds is relatively weak, so we only need 5 kJ per mole to break it. So basically it is about 22 times more than the comparison between covalent bonds and the hydrogen bonds. Now what's the distance between the proton right here and the oxygen of another water molecule to connect it with the hydrogen bonds? People did the research, it's at about 0.18 nanometer. So relatively it is longer than the covalent bonds by itself. Okay, so this is a chemistry structure. So we're going to go a little bit more detail right here. If you look at your textbook, the textbook at the page 4 and 5. Right here, if you read it, it says very briefly and using a little bit of hard sentence to understanding, is said the chemical structure of the water is sp3 hybrid, which is between of this hydrogen and oxygen, and they will be form a so-called tetrahedral dimension. So this is a little bit hard to understand what this means. So we want to explain this one to you a little bit more detail for you to understand the sentence there. So this is, go back, we talk about the electron sub-layer orbital arrangement in our first class. And this theory is coming from Linus Pauling, a great American chemist. To talk about the detail, and he won the Nobel Prize later on. So, what a story it is. When Linus Pauling go ahead to do the study about hybridization, he did not start it to do with water. He started to do is with a very simple, much more simple chemical, which is CH4, that is a methane. So what it looks like, this is we talked about already. This is looks like 4 hydrogen, each have 1 electron, and then you have a carbon, and the carbon has 4 electrons in the outer layer. So they could be combined. What is combined going to be looks like? This is C. It will be looks like kind of like that. Okay, they shared, and that is method. And this is, by the way, we call it a Lewis model. Now, why he wants to do this guy? Because in the older time, this methane is fermented from the human or animal fecal sample, and they could become an energy resource. So in the older time, people are using methane even to generate electricity. Even in lots of the Asian countries, back in 1920s, 1930s, they're still doing that. So that's why it's a research target. So this is a Lewis structure. Now we want to look at some detail about the sub-layer orbital, what it looks like. Okay, so let's talk about this carbon. Okay, we know the carbon, what it looks like is 6, 12. So that electron arrangement should be 1s2, 2s2, and 2p2. So what it looks like? We draw it, the second one and the third one. So it becomes 1s, 2s, and 2p. So based on Pauling exclusion policy, up, down, this is Hans rules, up and up. And we want to draw it in an opposite direction, which is from, instead we draw it horizontally, we're going to draw it perpendicularly, okay? So remember, when we talk about the arrangement of the electron in the sublayer orbital, we talk about the energy. Minimum policy is always from low to high. So what is it going to be looks like if it's from low to high? This is 1s, okay, and this is 2s, and then here it is 2p. So up, down, down, then go here, will be up and up. Now, by the way, all of these right here, what we call this stuff? These we call valence electron, because it's going to connect it with hydrogen. So let's say a hydrogen is right here. So a hydrogen is right here. It is easy, only up. This is H. Now, they start to do something. They start to see the morphology. Before he come out with this theory, he do the chromatographer to see the morphology of CH4 first. What do you find? It's very interesting. I can draw a brief picture, okay, not that nice. Center is C, then the outer layer is going to be H, 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 and be shared. So we draw it again. Shared, shared. What do you find? This angle is 109.5 degrees. So this comes out something interesting. Let's say the two S and two P, the valence electron, just stay like that, And then I have a hydrogen, a proton, electron goes in. They connected. Let's say it's not going to have this guy comes out. Which means if the electron doesn't do anything, for the valence electron of the carbon doesn't do anything, then the H cannot combine with them, become this dimension. So there definitely something happened here. So what's that? This is what you mentioned about hybrid. What's a hybrid happen? They definitely have a mixture between S and P. And what it looks like is sp3. So become up, 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 and up. That's called sp3 hybridization. Because once this comes, what will happen? They can go, they can go, they can go. And this comes with a hydrogen, which is this guy can go there, this guy can go there, this can go here, this guy can go here. That is called sp3 hybrid. Okay, so he found it. Then he did some research about the water. Okay, water, we know it is H2O. It's a connection between H and O. So let's talk about this O. What's oxygen looks like? Is 816. That means they have 8 electrons. What's the sublayer orbital looks like? 1s2, 2s2, and 2p4. Okay, so what it looks like? We draw it up, down. That is 1s. This is 2s. Up, down. Pauli exclusion policy, the Hans rules. 2p will be up, 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 and down. Okay. This is the key right here. Okay, let's draw it again. Based on minimum energy policy. This is from lower to high. And this is energy, okay? So, it will become, go over here, this will be 1s. Up, down. comes above here, it will be up, down, that is 2s, and then goes here. What is it going to become looks like? Up, down, up, and up. Okay, looks like that. So, once this happens, at the same time, he found this is CH. What's the water dimension looks like? So water dimension looks like this, 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 and that. And I want to draw it beautiful. So they have a little bit right here, a little bit right here, a little bit right here, a little bit right here. Okay, so you have a lone pair electron right here, and this will be connected with H, this connected with H. What is the angle? 104.5 degree. 104.5 degree. These are the same. So, the Pauling sinks, they need to be the same hybrids as a meson. This makes sense, what this going to be looks like. When they combine together, okay, this is 2p. It will become sp3, 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 sp3. So, up, down, up, down, up. Rearrange will looks like that. So, this will be waiting for a hydrogen goes there. This is also waiting for a hydrogen goes there. And this too is long electron pairs, doesn't connect to anybody. So this is called sp3 hybrid. Now there's a question. The angle here is 109.5 for meson. How come you have 104.5 for water? So he have another theory. Because you have these lone pairs, is that right? The lone pair electron push, lone pair of electrons push angle, it says shrinks the angle from 109.5 to 104.5 degrees. That's what it is looks like. And this theory is 1952 Nobel Prize. It is very important. That's why I want to introduce to you. Now, in your chemistry class, you learned the other hybridization. Later on, they're going to do more and more, so they find there's other hybridization. So we just briefly conclude here. Okay. This is S, this is P. Okay. It could happen, which is called SP hybrid. What will be the SP hybrid looks like? Very simple. This is S, this is P, and we have 2P here. So what it looks like? Like a beam, like a two beam connect together. So what's the angle? What's the bound angle? 180 degree. Very simple. That's SP hybrid. We also could happen is SP2 hybrid. How it looks like? This is S and this is P. So what it looks like? One S, one P, and this is P separately. So what it looks like? This is simple. What is the angle? The bound angle. 120 degrees. Therefore, in your chemistry textbooks, they often have a table. This is number of group. And this is number of hybrids. And this is the bond angle. Okay, so what it looks like. This is, we call it number of the hybrids, we call it SP 120, and this is 1. And this is 2, SP2, oh sorry, this is 180. This is 120, and this is 3, and SP3, this is 109.5 degrees. That's what the table looks like. In the chemistry textbook, you have that table. But why this become 104.5 for the water? Because it's pushed the long tail of the electron, they pushed a little bit. This is true what you explain right here. Okay, that's the key. So that's the chemistry stuff I would love to you understand, and that's why I spend the time to talk about it. Okay, now let's move the camera a little bit, just right in the middle, and we cover it. Make sure we cover. We're going to talk about the chemistry, for the chemistry material of water for the application. This is a pure chemistry. Okay, so that's going to be number 3. So first of all, we want to discuss hard water versus soft water. So this is relatively easy, so I'm going to move on this direction. Because otherwise there's not enough space. So what is hard water? What is soft water? We are talking about is amount or concentration of calcium and magnesium. And the United States do have a regulation for that. But different places is different, the concentration. So basically the calcium, the range is 40 to 80 parts per million, ppm. And magnesium is a little bit lower, is 20 to 30. Some places is 40 parts per million. So what is hard water? Pond water is hard water. It's undrinkable. Ideally, it's undrinkable. Now another reason is pond water, if you do not do anything, from a microbiology standpoint, there is fecal coliforms in. That's another thing from a microbiology standpoint. But from chemistry standpoint, the amount of the calcium and the magnesium is higher. So what is soft water? Municipal drinking water. Okay, your drinking water ideally is soft water. Now there is 2 different categories. Talk about the hot water. So number 1, we call it temporary hot water. What means temporary hot water? Because the components of calcium and magnesium is calcium carbonate or magnesium carbonate. So we know the chemical reaction, it could be reacted with water in a high temperature. Basically you're using boring methods. It will cause precipitation of calcium hydroxide and with carbon dioxide release. And the same as the magnesium carbonate reacted with water in a very high temperature, that could become magnesium hydroxide and also the carbon dioxide will be released. And of course, this will cause precipitation. So this is what happens is, in your home, if you have a, let's say a hot pot looks like this, okay? And you put the water there. Let's say you put a pound of water, then you boil it, what are you going to see? Couple weeks later, you see this very heavy precipitation. This is actually calcium or magnesium. This precipitation could be magnesium or it could be calcium. Okay, that's a temporary hot water. Now, we also want to mention there is permanent hot water. So permanent hot water, which means if the calcium and the magnesium is calcium chloride, calcium sulfide, magnesium chloride, magnesium hydrosulfide, and that could be not removed if you're simply using boring methods. Now, of course, there are some other chemical methods you can remove it, but from a chemistry standpoint, if you cannot simply using boring methods to remove them, we just call them, it's a permanent hot water. Okay, so this is question number 3. So topic number 3 is hot water versus soft water. So next one, what we want to mention is free water versus bound water. Okay, everybody knows what is free water. Free water is free available water in the food products. Can be made as using as a solvent. It could be generated through centrifuge. So let's say you have a food products. You put a meat there. You do a high-speed centrifuge. Let's say 10 multiplied by 10, 1000 G. For 10 minutes, what are you going to see? The water going to come out at the end. This will be the water. Of course, there is a precipitation here. So free water could be generated through centrifuge of a food products. It also could through filter paper. So let's say I put a paper there, and I put a chunk of meat in here. If I press it, you see the drop in there. Okay? That's free water. Now, what is bound water? What is bound water? This is people does not recognize it. Number 1, this is a water cannot use as solvent to dissolve other chemicals. This is water unremovable. And very interesting, this water is unfrozen at minus 20 degrees Celsius even. Now, how much of the bound water in a food products? In meat, it is around 11.6%. Fresh produce, kind of interesting, even fresh produce is 90% of them are water. About like 5 to 6% of bound water. Now let's talk about another product which is egg yolk or egg yolk. How many of them are bound water? Around 0.4 gram of 1 gram is bound water. So that's actually pretty high, 40% almost. Now, Sometimes there is a new technique tools we can do differentiate free water and bound water magnetic resonance. Okay, we call it using nuclear magnetic resonance methods. We could differentiate free water and bound water. Now, we're also going to be saying real quick, the bound water, usually it's in monolayer. At monolayer, most of those are bound water. Okay? So these are the topic number 4. So next one, we're going to make a big here. Moisture content versus water activity. This will be a huge important topic for the chemistry. A couple of years ago, I have my first graduate students coming, so I asked a simple question. What is water activity? She didn't even think about that, so she said, that is the amount of the water in a food products is water activity. But the answer is wrong, and it is completely wrong, because she messed up with the concept between moisture content and water activity. So we need spending the rest of the class, almost a half an hour to 40 minutes, we want to talk about this so you can understand really well. First of all, let's talk about what is moisture content. Okay, moisture content, very simple. This is amount of water in food or food products in foods, we just say. However, there is something we want to emphasize, you should understand. Every food product, let's say I draw a circle. There is 2 different parts. One part, it's water, it is wet. Okay, another part, it is solid. I won't say it's wet, I'll just write water there. It's simple. It is water and solid. Let's say our food products. This is just a model. Does not mean it's going to be 25%. Okay, so water and solid. When we talk about moisture content, there are 2 different measurements. Number 1, we call it dry base. What's going to be the dry base looks like? It is amount of water divided by amount of solid parts. So which means it is that 1/4 of a circle divided by 3/4 of a circle. So I just do like this, okay? So this means this part, and that means is this section. It's not draw very well. I'll just draw like this. This is dry base, easy to understand. Second one, wet base. What is a wet base means? Slightly difference. Amount of water divided by amount of solids and water. So this is very important. Lots of the for the chemistry publication, you see the WT percent. What this means? Wet base. So what it gonna be looks like? This will be this section to divided by the whole thing. Okay. Divided by the whole thing. So I'm using very easy drawing to let you know about that. So that's dry base and the wetter base for moisture content. Moisture content, we also want to mention, when a food product is exposed in an environment, it will be reach a balance of absorption and desorption. So, water, moisture content of water in the food products, usually we also call it equilibrium moisture content. Acronym EMC. The detail we'll talk about next week. Okay, that's moisture content. Second topic, water activity. First of all, water activity using AW to express it. What is water activity? In my microbiology class, we talk very briefly, and you see all those biology classes, you talk about the water activity also. You just call it available of water can be used by live body. Microbiology, plants, animals, especially microbiology. They just write the sentence like that. This is a very abstracted concept. Now, what is water activity? If we want to talk about the detail from the physics standpoint, water activity equals partial vapor pressure of foods. I will not say just say of foods. I will say above foods divided by partial vapor pressure of pure water. Now the question here is, lots of the textbook write this. What this means? Okay, now we're going to explain it. Okay, what this means. We need to draw a closed vessel. Like this. Above, we also draw a closed vessel, like that, corresponding to everything. Let's do a pure water first. This is pure water. In a closed vessel, we have a pure water, we put the water there. What will happen? Some of the water will stay in the solution, like this. However, there's a lots of the water molecule are going to flee away, like that. And they could flee away, they could go down. When they flee away, we call it evaporate. If they go down, we call it condensation. Now, what is condensation? Said very simple. In a very raining day, you have a top ceiling of the roof, and you go back home, you see it is dripping. You see the water is there. So drips there. This is a very example of condensation. Okay, so some gonna go down, some gonna go up. At the end of the day, they will reach equivalent. Equivalent. Equilibrium. Okay, equivalent. Which means the evaporator condensation will be basically balanced. You can understand. Therefore, it will generate a pressure here. Will generate a pressure. And this pressure we call vapor pressure. Now, the vapor pressure affected by what? Affected by what? Temperature. So, if we assuming there is a heater right here, there's a heater here, let's say. We're heating it. Or we put the closed vessel onto a fire to let them heating. What happened? This vapor pressure will be increased. Now we know outside there is atmosphere pressure. What is the one standard atmosphere pressure? The value 1 equals 1.013 multiple 10 the power of 5 Pascal. What will happen if vapor pressure equals atmosphere pressure? It's a very simple question in the physics. It happens boring. Is that right? It happens boring. So that's what the vapor pressure it is. And we are going to talk about the boring real quick. That's what the vapor pressure looks like. What it looks like. Now, we already talked about that. This